we were talking about Taylor polynomials. So I'd like you to find the Taylor polynomial T3 of x for the function inverse tangent centered at a equals 1. Okay, so first of all, why can't you use your Maclaurin series that you know for inverse tangent? Because it's at a equals 1 and the Maclaurin series is centered at a equals 0. Okay, so if you're going to do T3 of x, that means you're going to have a third degree Taylor polynomial, which means you need how many derivatives? I think you need 3 because the original function is the first thing. So first you have f of x is inverse tangent. And so f of 1 is inverse tangent of 1. Do you guys know what that is? Pi over 4. Yep. Okay, the derivative. Trevor, could you put your computer and stuff away, please? Thank you. What's the derivative of inverse tangent?
1 over 1 plus x squared.
1 over 1 plus x squared. Great. And so then f prime of 1 is equal to?
1 over 2.
Great. Okay, if these derivatives get super ugly, you can use things like Wolfram alpha to compute them because like the point is just how you find a Taylor polynomial. This one's not so bad. Technically, f prime of x is the same thing as 1 plus x squared, that quantity to the negative first, right? So taking the derivative of that uses what rule? The chain rule. So it'd be negative 1, stuff to the negative second, and then times what from the chain rule? 2x. Wonderful. So negative 2x over 1 plus x squared squared, and f prime prime of 1 will equal, I can't reduce fractions in my head, negative 2/4. Is that right? Negative 1/2. I don't want you to waste your time finding the derivative of that thing. It's just ugly. It's going to involve the quotient rule. It's going to be gross. Okay? So you are totally allowed to Wolfram alpha that, or we'll just give you easier stuff where the derivatives don't get nasty. So the third derivative is 6x squared minus 2 over 1 plus x squared squared. Trusting my colleague here, so hopefully she's right about this. And assuming that's correct, what's the third derivative at 1? So 4 over...
4, yeah.
So I think she made a right O on her thing. I think this is supposed to be cubed. Does anybody have a Wolfram Alpha app on their phone where they could check that real fast?
Not many moments.
Not this moment. I can look on my computer. So anyhow, let's assume it's cubed because she also says that plugging this in, she gets 4/8, which is a positive half. So assuming that this is correct, find me T3 of x. Like you guys do that while I look up and make sure that derivative is correct. Don't forget about the whole factorial stuff.
It's, that's the derivative
Negative 2x over 1 plus x squared squared. The denominator is supposed to be cubed. I was right. Okay. So what I wrote on the board is not wrong. What's in the notes is wrong. Okay. So this is equal to f of 1 plus, then what comes next? F prime of 1, yep, and that would be technically over 1 factorial, but 1 factorial is just 1, so no big deal, right? Guys, do you have a question back? Okay, times x minus 1 plus, then what's next? Times x minus 1 to the second. And then the last term that we have in this third degree thing is third derivative at 1, right? Over, What do you think the thing that students most often forget in this process is?
multiply out the factorials?
I think often I've seen students just forget them altogether. Is it just because they forget that they're there? Yeah. That last one should be cubed. Yep. Thanks. Okay.
Do you want us to solve that all out and get it over?
Nope. I just want you to plug the numbers in. So like f of 1, for example, is pi quarters, right? Yep. F prime of 1 is a half, so you've got a half times x minus 1. You don't need to distribute that, you can just leave it in this form. I do kind of care you don't have fractions over fractions, that's kind of like bad math grammar. So don't write negative 1/2 over 2 factorial. Instead write minus 1 over 2 factorial times a half. Does that make sense why that is that way? Okay. And then on the same vein, what should the last term be? Is it positive or negative, first of all? Positive. And then we'll have 1 over how many factorials? 3 times a half x minus 1 to the third. And that's good enough. I think it's modestly obvious at least nothing's going to cancel. Does that make sense?
So you want to estimate 1.1, you just plug it into this?
Yep, if you wanted to estimate inverse tangent of 1.1, you just plug it into this. I think we're asked to estimate inverse tangent of 1.5. So I'm just going to do that right here because I've got this polynomial here. So this is your part B, which says to use T3 to estimate tan inverse of 1.5. And tan inverse of 1.5, 1.5 is close-ish to 1, right? I mean, depends on how close it gotta be. It's about equal to plugging into this thing, 1.5. So that's pi quarters plus a half times a half. Do you buy that? Because 1.5 minus 1 is a half, right? Minus a quarter times, and then plus, this will be a 12th great times a half to the, and I see another mistake in my notes, so this is pi quarters plus a quarter minus a 16th plus a, well, that's going to be 8. 8 times 12 is 96. Okay. I'm going to leave it like that, and we'll say that you should get a decimal and give me an answer, but I know the one that I have here is wrong because there's a plus sign, but there should be a minus sign. Okay? But that's...
This should be a minus sign?
Yeah, I am, actually, because you do 1.5 minus 1. There's no reason for that minus sign to go away. Is there? Do you see any reason for it to go away? No. Okay. So what do I have? I've got pi over 4. What comes next? Plus a quarter.
Minus a 16th.
Minus a 16th, okay.
Plus 1/96.
Plus 1/96, okay. My computer tells me this comes up to be 0.9833. 0.9833. There's more change, but that's to start. Awesome. Okay. And part C asks you to find tan inverse of 1.5 exactly, as in using your calculator. So why don't you do that? Make sure your calculator is in radians. Tell me what your calculator gives you.
I've lost a couple points on tests over the years because of that.
Probably not in this class though, right?
No, that was back in, geez, I think it was geometry class in high school.
Yeah, that's a tricky thing there.
Geometry was a fun class.
Well, we've gone back and forth between ratings and degrees.
Anybody dare to tell me their answer? Go ahead.
0.98279.
0.98279, so it'd be 2.8 would be all right, right? Round up?
Yeah.
Yeah, okay. So here's our estimate. Here's our, so we're actually not by all, we're not off by all that much, would you say, right? I mean, it's
5 10,000s? Roughly 5 10,000s?
roughly 5 10,000s, yeah. Just I think that's not that bad. If you want to make it more, if you went out to like T6, it's going to be like pretty accurate already.
Yep.
Yeah, so, isn't that, like, is this like a little bit interesting?
Yeah.
Okay.
Of course, if you were on the planning board for Apollo 11 and this was your error, then that could be bad.
If you were on the planning board for Apollo 11 or, Lord heaven forbid, Apollo 13,
Yeah.
I think that they probably had tolerance levels set up.
Or
Yeah.
they
Yeah.
just use calculators.
Oh, back in Apollo 13 happened, they did not have calculators.
Yes.
Oh, you guys are so young. You are so young. Look at that movie. Like, you want to go back and watch that movie? They have calculators who are people. As in, that was their job, was to do calculations. Computers were a new thing. This calculator thing did not exist.
Well, I mean, I would expect it to be
Huh?
huge.
They have rooms.
They had rooms full of people. It was crazy. Go watch the movie and you'll see them. Like, and yeah, but what was the Apollo, 1960-ish, right? When was Apollo 13?
Well,
Well, it must be later.
Not the one that succeeded, right?
Yeah, it was the one they made a movie about. Anyhow, moving on. I'm too distractible. Okay, we did this. We did this. All right. So now we have a question about, you've seen some Taylor polynomials, and one, I think, really reasonable question to ask is how accurate are they? Does that make a really reasonable question? Like, how many terms do you need to get a certain level of accuracy? Because you can tolerate some level of inaccuracy, and like how big, what must be the kind of, like, is it Taylor 5? Is it a 5 degree or 6 degree? What's good enough? So the way we talk about the remainder, so the remainder is the difference between the actual minus your estimate, right? That's like the whole general form.
Apollo 13 was 1970, by the way.
Oh, okay. Off by a decade. Actual minus estimate. Okay, so we're using a Taylor polynomial to approximate a function f. How good is this approximation? So in this case, instead of actually having numbers we're comparing a function. That's the actual thing, right? What is the thing we're using to estimate this? The Taylor polynomial, right? Which is the Tn. It is kind of a sum, but it is a finite sum. Does that make sense? When I hear the word sum, I kind of default to infinite. My brain. Okay, so here are three possible ways to estimate the size of your error. You could actually, like, take your function f of x, subtract the function Tn of x, and you could graph that absolute value on the interval, and that would tell you, like, how big your error was. I dislike that way because it makes you, like, actually graph. I think it's just annoying. But, I mean, graphing in real life is a really good way to look at stuff, because they're good graphers these days. The other thing you can do is, if it ends up that you have something that is alternating, you can use that AST remainder theorem, which is a really sweet theorem. We like that remainder theorem. And if you don't have things that alternate, you can use something called Taylor's inequality. And this inequality is proved in your book. I'm not going to prove it to you. But what this says is that the absolute value of a remainder is less than or equal to a constant m, which we'll talk about in just a sec, over n plus 1 factorial, so one more than what you left off at, times x minus a to the n plus 1. So, first of all, what is that m thing? So, this m thing is a number such that your next derivative is always less than or equal to it. So, like, if you were looking at the remainder for a 4th degree Taylor polynomial, you look at the 5th derivative to find your m. You just go one more derivative down. Okay? And you say, okay, when is this 5th derivative my biggest? So, like, if this was n equals 4, this would be the 5th derivative of x. And maybe it's an easy function you can look at and you can say, okay, on my interval that I care about, when is this thing the biggest? And then you also will look at when is this x minus a to the n plus 1 the biggest. I think the easiest way to do this is with an example, because there's a lot of numbers there and you need to see specifically what they mean in terms of an example. So let's do one. Okay, so we have three parts. We have part A, which is to approximate the function f of x equals x to the 2/3 by a Taylor polynomial with degree n equals 3 at a equals 1. Everyone can do that, right? Yes, okay, let's do that then. So part A. So our f of x is x to the 2/3. What's the first derivative? Don't fail me now, come on.
Negative 1/3.
Mm-hmm. Great. Second derivative is Ready, set, all at the same time, go.
Negative 2/9.
X to
X
the
to the negative 4/3.
spectacular. And one more. Positive, positive 8 over 27, right? X to the,
Negative 7/3.
yes. Okay. And what number are we plugging into them? 1. So f of 1 is 1. F prime of 1 is
2/3.
great. Second derivative at 1 is negative 2/9, right? And the third derivative at 1 is,
8 over 27.
yep, awesome. Okay. So then T3 of x is f of 0 plus f prime of 1, x minus 1, plus f prime prime of 1 over 2 factorial, x minus 1 squared.
Should the first one not be f of 1?
Oh, it should be f of 1, yes, I don't know, I'll fix that in just a second. F prime 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 of 1 over 3 factorial, x minus 1 cubed. Yes, of course, the first thing should be f of 1. Let's just see if I can not use the huge eraser. Look, I succeeded. Okay.
Making you mistake often enough and you win.
Hopefully. All right, so now we input all of the things. So we have, for this case, T3 of x is 1, 2/3 x minus 1 minus 2/9 times 1 over 2 factorial, x minus 1 squared, plus 8 over 27, 1 over 3 factorial, x minus 1 to the third. Is some stuff going to cancel? On a previous one, stuff didn't cancel, right? But in this one, will some things cancel? For example, what? Just look at the the coefficients I care a teensy bit about. Do I think that first, the second one becomes negative 1/9? And the last one, well, this 3 factorial is really 3 times 2, right? So the 2 can divide by that 8, yes?
So it'd be 480.
It'd be 481st. So if you can do some canceling, I'd like you to do that. Okay. So that's part A. Now part B here says to use Taylor's inequality to estimate the accuracy when x lies in the interval from 0.8 to 1.2. Okay, so the first thing we need is we need the fourth derivative. Does that make sense? Because the inequality says that Rn of x is less than or equal to this m over n plus 1 factorial times absolute value of x minus a to the n plus 1, where m is less than or equal to the absolute value of the n plus first derivative. Okay. Oh wait, sorry, I put that inequality backwards. This should go absolute value of m plus first derivative, n plus first derivative, thank you, is less than or equal to this m. Okay. So in our case, n is equal to what? We found the third degree Taylor polynomial, right? So you need to look at the fourth derivative, which is equal to what?
Just keep going from our third derivative.
Just keep going from our third derivative, yep. We have
Negative 56.
over 81, right?
That seems like that should be able to simplify.
To the negative 10/3. I didn't simplify it, so let's just leave it as negative 56 over 81 x to the 10/3, just like that. And then with that, let's look at how we deal with all of these pieces. So what's the easiest part to deal with in that fraction on the right? Like thinking about the m, the n plus 1 factorial, or the x minus a to the n plus 1 thing. You know what n is, right? So I think the 4 factorial is the easiest bit of that, right? Let's look at the x minus a to the n plus 1. So specifically, we care about the interval from 0.8 to 1.2. Question, why? Why is that the interval I'm looking at?
Because it told us that.
Because it told us so. Okay, so you're going to be given an interval to look at. You'll be given some kind of accuracy. On that interval, we're looking at x minus 1 to the 4th. Okay, so we know that, here's a little side work, 0.8 is less than x, which is less than 1.2, right? I have something, I want to know something involving x minus 1. So how can I change this inequality so that, and this really should have or equal to's on it, but it doesn't really matter. How could I make that so I have x minus 1? Almost, not add 1, you would subtract 1 in every single place in that inequality, right? So you'd get minus 1, minus 1, minus 1. So that's what, negative 0.2, right?
Yes.
Is less than or equal to x minus 1, which is less than or equal to 0.2. And isn't that the same thing as saying the absolute value of x minus 1 is less than or equal to 0.2? So therefore, x minus 1 to the 4th is less than or equal to 0.2 to the 4th power. Okay?
We don't have to math.
Does that make sense, though?
I was just trying to do that in my head.
Don't worry about doing that in your head, okay? So we've taken care of that part of the inequality, okay? So there's one piece. Now we need to find that m. So look at the absolute value of your 4th derivative, which is the absolute value of 56 over 81 x to the 10^3. Okay, and we're going to look at this on the interval from 0.8 to 1.2. And it's just a very general thing, but what has to happen to this function when you plug in bigger and bigger numbers? Trying to make a hand gesture to give it away. As you plug in bigger and bigger numbers, this function gets smaller, doesn't it? So on the interval from 0.8 to 1.2, when is this function the biggest?
0.8.
At 0.8. So this is less than or equal to, and I also got rid of the negative sign because it doesn't matter, 56 over 81 times 0.8 to the 10^3 power. So you just think yourself that, okay, well this function that I have is decreasing, therefore it's biggest at the left endpoint. If the function you had were increasing, where would your at what endpoint would you be biggest? The right one. It also could happen someplace in the middle, correct? Yes.
So, so you're supposed to, write one
Because the question we have to answer with this is, I need a number such that this thing is always less than or equal to it on that interval. Like I want to figure out what is the biggest this thing could be on that specific interval. And the biggest this thing could be on that specific interval is when I plug in 0.8. Does that make sense? And so which number you plug in, whether it be a left endpoint, right endpoint, something in the middle, depends upon if your function that you're looking at is a decreasing thing or an increasing thing, or has someplace highest point in the middle. You could also graph this thing and look for, like on the interval, look for where is it the biggest. Okay, and then you're pretty much done. So the absolute value of R3 of x is less than or equal to 56 over 81 times 0.8 to the 10^3 over how many factorial?
4.
4 times 0.2 to the 4th. which comes out to be approximately 0.000009697.
Oh, that's ridiculously small.
Yeah, and also, the remainder is less than this, which means this is like an overestimate of how much it is. It could be even better. That's a worst case scenario kind of a thing.
Would you plug in 1.2 to find best case scenario?
That's a good question. I just wrote all over my thing. I only know that the inequality works this way, and I'm not sure that that gives you a lower bound, but it might.
Okay.
Does that make sense? Like, we usually don't ask you to say, like, what is the, usually you just ask, like, what is the worst possible as opposed to the best possible.
Okay.
So the worst possible, you can calculate for that.
Yeah, I guess the idea is if it's better than you expect, then that's just icing on the cake, so to speak.
Okay, yeah, that's fair.
Okay, and so let's just compare the two now. So that's what part C says, right? Compare the approximation and the exact value. So the exact value is 0.8 to the 2/3 power, which if you calculate it comes out to be 0.861773876.
Is that the exact number?
That's I trusted Jill. So, and T3, when you plug into that, it's about equal to 0.8618 271605.
So then we just put,
If you subtract those two, do you get a number that's less than this? It looks kind of suspicious to me, like I have one extra decimal or something like that. 1827.
the exact is the 77.
Yeah, exactly.
76. So you subtract the T3 from that, right?
Yeah, well, you can do it either way, you just get a negative number in one of the directions, and you absolute value it. But I can't do that kind of decimal subtraction in my head, I'm
You
not
also
that.
get different absolute values.
3, 2, 8, 4, 5. I think better.
It's 10 to the negative something, right? So what'd you get? When you did T3 minus 0.8 to the 2/3, tell me one more, just say it again.
5.32.
5.32 times 10 to the,
Negative fifth.
that's fine, I think, isn't it? Because this really is, decimal goes backwards 5 spots, so that's 4 zeros. 2, 3, 4, 5, 3, 2. So that is less than this number, yes? Okay, awesome. All right, ready for another one?
You start here just for a moment, you go right back down.
Hmm?
You surface for air for a moment, you just go right back
I'm
down.
sorry. All right, so how about sine of x at pi 6 with a polynomial of degree 4? Use Taylor's inequality to estimate the accuracy of the approximation of this when you have x between 0 and pi thirds, and then use it to estimate sine of 38 degrees. Okay.
Degrees this time.
Well, we're going to convert those degrees into radians, so sorry. We start there. So first, let's find the approximation. We call this part A. How many, if we're using n equals 4, we need to find 2 the fourth derivative, right?
So on the last one, is that like a good answer or like?
I think, so you're asking, like, is that accurate enough that you would need to do more? I think it depends on
Is that
the,
good or is that bad?
I think it depends on the context of your situation and specifics. So I think that for some things, being off by 1/10 is okay, but for some things, you need to be even closer than that. I don't know enough about, that would be kind of like an engineering question. Like, how accurate do we need this thing to be? And I don't know the theory of what's accurate enough for different situations. But it's a really good question, though. Okay, so we have f of x is sine x. First derivative is?
Are we finding it's the fourth derivative?
Yep.
Okay.
Second derivative is?
Negative sine x,
Third derivative is?
negative cosine x,
Okay, and we're almost done.
sine x.
Fine. Lots of cosine.
Applied laws of cosine.
No, positive cosine, negative sine,
Yep.
negative
I don't
cosine.
know how you'd apply the laws of cosine.
You don't apply the law of cosines to this. Okay, this doesn't happen. Oh, I know pi 6 is not your favorite number. So what is sine of pi 6? 1/2. Cosine of pi 6 is, okay, second derivative at pi 6 will be -1/2, right? Third derivative at pi 6 is, and the fourth derivative at pi 6 is 1/2. Okay, so T4 of x. I'm just going to go ahead and start plugging in what stuff is. So first we plug in f of pi 6, which is 1/2, plus √3/2 times x minus what? And then next comes a minus 1/2 factorial, and then another 1/2 x minus pi 6 to the second. Next we have a negative 1/3 factorial, √3/2 x minus pi 6 to the third. And finally, 1/4 factorial, 1/2 x minus pi 6 to the fourth. Yeah.
Since, we know that we have to find like one more, wouldn't we just add or find the derivative?
Yeah, like if you know you're gonna have to find one more derivative to use the estimation thing, you could just find the fifth derivative. Yeah, that's totally fine. Okay, I think that we'll just leave T4 like that for now. On your homework, let's say you gotta multiply together those coefficients and just simplify it to make your grader's life easier. What do you mean by that? Like, do 4 factorial times 2, that's all. Okay, so that's the Taylor polynomial. Now we're looking at the interval from 0 to pi thirds. So on the interval from 0 to pi thirds, we have 0 less than x less than pi thirds. Or equal to, sorry.
48.
Yeah, so here's the thing. Remember how we got last time we got to be x minus 1? By taking away 1 from each spot, right? How are we going to get this thing to be x minus pi 6?
Subtract pi 6.
Subtract pi 6. And if you do pi thirds minus pi 6, a third minus a sixth is a sixth, right? I know you can't all do fractions in your head, but I think you can probably do that one. Okay, so this implies negative pi over 6 less than or equal to x minus pi over 6, which is less than or equal to positive pi over 6, or the absolute value of x minus pi 6 is less than or equal to pi 6. These intervals are doctored to work out this way. Like, they're doctored to be symmetric, so you can easily make this conclusion. So in this case, we care about x minus pi 6 to the what power? To the fifth. That's going to be less than or equal to pi 6 all to the fifth power. The next thing we care about is looking at the fifth derivative. So this shouldn't be very hard. What is the fifth derivative? Cosine. And it doesn't matter what interval I give you. What is the biggest cosine could be? 1. This is less than or equal to 1. So you let m equal to 1 in that equation that you have. That's your constant. Okay, then R4 of x This is less than or equal to m over n plus 1 factorial x minus a to the n plus 1. And what numbers go in for all that stuff for us? What goes in for m? 1. What goes in for n? 4, so that becomes 5 factorial,
Or 120.
or 120, times pi over 6 to the 5th, which is about equal to 0.0000328.
That's a much worse error.
It's, yeah, we're off by a bit more. That certainly is in 5 decimal places. Okay. All right, part C. So is everyone okay with how I found, I mean, there are 2 things you've got to worry about with that error. You've got to worry about the x minus a to the n plus 1 power. That's not so bad, right? And then the derivative thing, you just have to look and see when is my derivative the biggest. And hopefully it's something that's obviously increasing or decreasing. Sines and cosines are also fair game because they're super easy to estimate highest and lowest values of, right? Okay. Okay, part C says to estimate sine of 38 degrees. Now this formula has built-in radians because those pi 6 are in radians. So if you're going to estimate sine of 38 degrees, you're going to have to convert that into radians. So 38 degrees, how do you convert that into radians? Multiply by, I think it's pi over 180, right? Okay, or 2 pi over 360, same thing, right? So we have 38 pi over 180, which reduces to 19 pi over,
290.
over 90.
So way to make that better. I don't know if it goes past that.
It doesn't go past that. One thing that Jill did was she wrote it as pi 6 plus 2 pi over 45, but like you don't have to do that. Anyhow, let's just plug in 19 pi over 90. So T4 of 19 pi over 90.
Wait, don't we have to make sure it's accurate to 5 decimal?
We can do that by comparing to the actual thing, because this definitely didn't give that to us. Does that make sense? Because 5 decimal places of accuracy would be 5 zeros and then a 5. And I think that's either a function of this question being a little bit wonky, or maybe they want you to compare your estimate to the actual answer. When you plug in 19 pi over 40 into that equation, the Taylor polynomial, you get, it's approximately 0.61566. And how you know that this is accurate to 5 decimal places is you find sine of 19 pi over 90 in your calculator, and that comes out to be about 0.61566144753. So then the question is do the first 5 places match? Yes.
And the number after that is less than 5.
Yes, exactly. Cool. Yes.
On the last part of part B, where you switched it from the m over n plus 1, how did you get the 1 over 5 factorial by pi 6?
Okay, so I got the, whenever, so this should have been an n, right? And this is always 1 more. So like if you did the 4th degree Taylor polynomial, this number is always 5 factorial. It's always 1 more. Did that answer it? And the same thing for the power, right?
Yeah.
So so what I should have just done here is instead of, when I wrote R4, I should have wrote 4 plus 1, and 4 plus 1.
But how did you go from absolute value of x minus a to
Oh.
pi over 6?
Okay, that's right here. So we have x minus pi 6 is less than pi 6.
Okay.
And so if you raise it to the 5th power, it's less than that number to the 5th power.
Now I got it.
Okay, great. All right. Anything else? It's tricky. This is why this is like a take-home quiz. This will not really appear on your test in any sort of large way, okay? Like it's more of a like take-home, because you need calculators to do the rest of it, right?
Yeah.
So, yeah.
So if we didn't know the actual value of,
If you didn't know the actual value and all you had was this estimate, my first inclination would be I'd better add more terms to that Taylor polynomial because this does not at least guarantee me 5 decimal places of accuracy.
so would we have to like solve for n in that equation?
We are going to do that in very specific cases like this next example. So, yeah, do you guys' question was, it was kind of like, how would I figure out what n I need to have a certain accuracy, right? That's what this is saying.
Oh, no.
Oh, man, right? Okay, so the tricky thing here is they haven't given you an interval and stuff. Oh, man, okay.
Figure that out.
You gotta figure that out, though. Okay, so we want to estimate e to the x, and we're going to use the Maclaurin series,
Which we actually know.
which we actually know, yeah, which is kind of nice, right? To estimate e to the 0.1 to within 0 point, many zeros and a 1. Okay, so, so we have Rn of x is less than or equal to the absolute value of the n plus first, well, less than or equal to, sorry, m, over n plus 1 factorial x minus a to the n plus 1.
Okay, just so I have this right, e to the x is equal to the infinite series from n equals 0 to infinity of of x to the n over n factorial?
Mm-hmm.
Okay.
Where the absolute value of fn plus 1 of x is less than or equal to some number, m. Hopefully I didn't get that backwards again.
No, that's correct.
Okay. Whew. Alrighty. Okay, so first of all, what do we know? We know that a is equal to 0, because we have Maclaurin series, so that's easy to fill in. Okay, can we look at the whole derivative thing then? So we're asked to estimate e to the 0.1.
So we gotta figure out how many derivatives we need to go to and then.
Yeah, so we need to figure out something about the derivative. So what is the derivative of e to the x, no matter what? It's just e to the x. And if we're trying to estimate e to the 0.01 and we're centered at 0, we can say something like you're on the interval from 0 to, or even, anyway, 0 to 0.1 or something like that.
0.2.
It doesn't matter, but you're trying to estimate e to the 0.1.
Yeah, it's included.
So, and e to the x looks like that as a picture, right? So what's one number that you could use for a bound there?
0, 1.
Yeah, fn of x is less than or equal to, we'd be just about e to the first, right? That'd be okay?
Sure.
Which is approximately 2.71, so let's use that.
Still haven't figured out what our n plus 1 factorial is gonna look like.
Well, this is a whole guess and check thing. And actually, let me make,
There's no way to calculate how many derivatives you need.
you have to guess and check. So can I do something, just like be consistent with Jill? So what she did, 0.1 is way the heck over here, right? So 2.71 is super rough. Let's instead just say that we looked at this graph of where e to the 0.1 landed, and let's just say we'll use 1.5. So that's what the guess that she put. Okay, then you have Rn of x is less than or equal to 1.5 over n plus 1 factorial. And we have x minus 0 to the n plus 1. Does the Maclaurin series. So when is this biggest? On 0 to 0.1. At 0.1, right? So this is the same thing as, or less than or equal to 1.5 over n plus 1 factorial times 0.1 to the n plus 1. And you want that less than 0.00001. You solved stuff like this in the previous lesson, and theoretically speaking, on your last take-home quiz, how did you find a number that worked?
Guess and check.
Just guessed and checked until you got one that worked, right?
We try like 6.
The first, well, I'll just tell you what the first number that works is, because it just takes a while to check. So, n equals 3 is the first number that works. If you do n equals 3, this expression, 1.5 over 4 factorial times 0.1 to the 4th comes out to be 0.12345 zeros 625. And that's definitely below that threshold, right? But not n equals 2.
Because E is ridiculous like that.
You get 0.1 to the 3rd, 1.5 over 3 factorial. This comes out to be 0.00025. So in our case, we found that n equals 3 is good enough. And some of that will depend upon how you pick your value for that m. Like if we had picked that m value equal to 2.71, we would have had to probably use a bigger n. But that's just because we grossly overestimated with our m.
So we would have definitely had at least the worst error possible.
Yeah. And sometimes what textbooks have done for stuff like this, I'm pretty sure what your textbook answer key does for this, is it uses e to the 0.1 for this value right here. Because that's the biggest that e to the x is on the interval from 0 to 1. But it seems kind of silly to estimate e to the 0.1, assuming you can know e to the what e to the 0.1 is. So, but you understand that this is the biggest that this function is on that interval? Yeah, okay. So if WebAssign is being funky on this question and making you like have the same n, I don't know if they make it the same n as them or an n that's bigger. Does that make sense? So you might have to use e to the right endpoint for that estimate of m to get the answer that they want. I haven't tried to see what the tolerance is in WebAssign for stuff like this.
It's better than it was though, right?
I hope so, I think so. Now the last thing I want to talk about is how do you use that alternating series remainder theorem to do some of this estimation, because that is definitely a lot nicer. So how many terms of the Maclaurin series for ln of 1 plus x do you need to estimate ln of 1.4 to within 0.001? So this is not a series you have to have memorized, but this is equal to, so one of the funky ones that doesn't actually begin at 0, they begin at 1, right? Starts at n equals 1 to infinity. Spectacular. N over n. Okay. So, how does ln of 1.4 relate to that function? This function, this ln of 1 plus x has a built-in like 1 plus some number in it, right? So to think about talking about ln of 1.4, we've got to make it into ln of 1 plus some number.
1 plus 0.4.
Ln of 1 plus 0.4. And that's going to equal a sum. N equals 1 to infinity. Negative 1 to the n minus 1. 0.4 to the n over n. And you should do a happy dance whenever your series is alternating. Is this series alternating? Yeah, this series alternates. So we're going to use the AST remainder theorem.
That's when we're starting to
Oh,
get fuzzy.
and since we're talking about an alternating series, remember that we have sort of -1 to the power component of that, and then we have the thing that your book calls b sub n. So what is b sub n in this case?
0.4 n over.
0.4 to the n over n. Okay. So we want, or we know that the r sub n of x is less than or equal to b, is it just bn or bn plus 1, which is 0.4 to the n plus 1 over n plus 1. We want that to be less than 0.001. And once again, this is not one of those things where it's easy to just like, sometimes you can solve for n, like using algebra to do so, but often it's just not going to happen. So the guess and check thing is the stuff you'll have to employ. Here I began testing at n equals 4. At n equals 4, 0.4 to the power of 5 over 5 came out to be 0.002048.
That was like slightly failing.
That's slightly failing, right? So then we'll check
It was fine.
n equals 5. And we have 0.4 now is going to be to the 6th over 6. And that comes out to be 0.123, I think 468. My decimal might be off by one place. We got 0.4 to the 6th over 6.
It's 3 zeros.
It's 3 zeros? Yeah, I suspected as much. So 3 zeros and then 68.
It's still better.
It's still better, and also I think it's good enough.
Yes.
Yes.
Yeah, it's within the thing you wanted to be within.
Yep.
What do you call that? Range?
Yeah, it's within the error tolerance or something like that. Yeah, it's in the range you want the error. So we would use, so now let's see, how many, it just says how many terms, right? So the answer to that is
Five.
n equals 5. Be careful if the question said to like give an estimate. Does that make sense? Because if it said to give an estimate, what would your estimate be? As in you have to actually do the sum. The sum from n equals 1 to 5.
That's be 0.00068.
0.0068 is the remainder, like the amount you're off by, but it doesn't tell you what the actual estimate of the value is.
So it would be T5.
It'd be T5, yep. Although I'm not, that T notation might also include having a 0th term, which this one doesn't. So I'm not sure how they, but I think T5 is reasonable to stay. There's just no T0 term. So it's 0.33698. Okay. I think we'll actually finish on time today for like the second time this semester. Okay. All right. Ready for the last one? Also AST? Okay.
No.
No. Okay, so use this alternating series estimation theorem or Taylor's inequality, but my goodness, if you ever have something alternating, use the AST remainder theorem is so much better. To estimate the range of values of x for which this has error less than 0.005. Okay, so cosine of x is equal to the sum from n equals 0 to infinity, -1 to the n, and then what's the rest of it? Because you have to have this one memorized. X to the 2n. What is the trick for memorizing cosine and sine?
Cosine is x to the 2n, sine is x to the 2n plus 1?
Yeah, and cosine, well, yeah, and I was thinking cosine is an even function, even powers. Sine's an odd function, odd powers. So that's my only trick that I've got, so you can hate on it if you want to. So we're going to use Rn is less than or equal to Bn plus 1, which we want less than 0.005. Okay, so what this bn plus 1 thing is, it's like the next term you've left off. So you can calculate it by actually plugging in n plus 1, or you can just look, what's the next term you left off?
X to the 5th over 4 factorial.
X to the 5th over 4. So this is like the 0th term, first term, second term, right? As you left the third term off. So B3, which is going to be equal to x to the 6th over 6 factorial. That's the next term that you're missing. Other than it would be negative, but this B part just takes care of positive parts into account, right? So you want that less than 0.005.
So it's less than or equal to.
Sure.
You multiply both sides by 6 factorial.
Yeah. So and also one thing is that we're looking at the absolute value of your remainder. So you probably should be looking at the absolute value of that, but anyhow. So we have x to the 6th is less than or equal to 0.005 times 6 factorial, which actually comes out to be 3.6. And then how do you solve for x? 6th root it. So x less than or equal to 6th root of 3.6, which is,
0.6?
no, 1.23799.
That's what multiplied by itself 6 times to get 3.6.
Yeah, which is something funky, right? Okay, so then what we have is that this absolute value of r sub n is less than or equal to x, which is less than 1.2379. I just wrote the wrong number.
Doesn't that have like transitive properties?
Yeah, so what it really has here is that we're not quite done, but what this really says is that x is in between that number on the positive side and also the same number on the negative side. And I don't think it matters if you put the or equal to's or not, we'll be that picky, but the idea here is that x could have gone both above or below, and that's okay. And these things will have this sort of symmetry to them. So, okay, look a minute early.